Welcome back to another explainer. Today we're diving into the incredibly beautiful, highly logical world of algebraic variables. Specifically, we're going to be looking at simultaneous equations. Now, if you've ever looked at a really complex situation with multiple moving parts and wondered, how do I actually find the undeniable truth hidden in all these numbers? Well, you are definitely in the right place. We're going to break down exactly how to take those abstract unknown variables and pin them down using structured, elegant mathematics. It's going to be great. But before we jump right into the variables and the algebra, I want to anchor our mindset with this really profound thought from the brilliant mathematician Maryam Mirzakhani. She noted that the beauty of mathematics only shows itself to more patient followers. And honestly, this is absolutely crucial for what we're doing today. Finding the value of an unknown variable requires following a structured process. It's not about just throwing numbers at the wall and guessing. It's about being patient, following the rules, and letting those logical steps reveal the final answer to you. Here is our roadmap for this explainer. First, the intersecting paths, then the elimination method, followed by the substitution method. After that, tackling nonlinear equations, and finally, real-world applications. All right, let's kick things off with Section 1, the intersecting paths. So, here's the core issue. Sometimes one single variable just isn't enough to describe a situation. Think about it. If I tell you that x plus y equals 10, well, x could be 5 and y could be 5. But wait, x could also be 9 and y could be 1. The possibilities are literally infinite. That's why we need multiple equations working together, simultaneously, to lock those variables into place and find the single mathematical truth. The rule of thumb, 2 unknowns require 2 equations. 3 unknowns, you need 3 equations, and so on. It's like a giant puzzle where every piece has to fit perfectly at the same time. And this brilliantly illustrates a real-world example straight from our source material. Check out this scenario. We've got 2 rival netball teams, and they have completely different game outcomes. Team A won 6 games and drew 8. Team B won 8 games and drew 2. Yet, despite taking these totally different paths, they somehow ended up tied with the exact same final league points, 26. So this leads us to a really fascinating question. Based solely on those stats, how do we find the exact point value of a single win, let's call that W, and a single draw, which we'll call D? Now sure, because we're dealing with sports scores, you might be able to just guess small numbers through trial and error. But what if those numbers were complicated fractions or negative decimals? We need a bulletproof, structured method to find these unknown variables reliably every single time. Now, you might be wondering, why not just draw a graph? And that's a fair question. Graphing is visually awesome because it shows us exactly where the paths cross. That intersection is our solution. But, as our source text warns, graphing often only gives us a rough approximation. It's pretty tough to read a tiny fraction perfectly off a hand-drawn grid, right? Algebra, on the other hand, gives us that pinpoint, undeniable accuracy we need. So that's where we're going to focus all our energy today. Moving right along to Section 2, the elimination method. Okay, this method is incredibly structured, and the goal is literally in the name. You want to eliminate a variable entirely. Step 1, if you need to, you multiply the equation so that the number sitting in front of one of your variables, the coefficient, matches perfectly. Step 2, you either add or subtract the entire equations together to cancel that variable out. Poof, it's gone. Step 3, with only one variable left standing, you just solve for it. And finally, Step 4, you plug that answer back into an original equation to find your missing piece. Let's actually see this in action. Looking at this specific example from the source material, we have 2x plus y equals 10 and x minus y equals 2. Notice those y terms? One equation has a positive y and the other has a negative y. This is great because we don't even need to multiply anything here. If we simply add the top equation to the bottom one, the positive y and negative y cancel each other out completely. They are eliminated. So we're just left with 2x plus x, which is 3x, equaling 10 plus 2, which is 12. And hey, if 3x equals 12, then x must equal 4. Once we know x is 4, we just plug it back into the second equation. 4 minus y equals 2, which means y has to be 2. Fast, elegant, and perfectly exact. Let's switch gears and look at Section 3, the substitution method. So sometimes eliminating just isn't the easiest path, and we need a different approach. Instead of matching up columns of numbers and canceling them out, substitution is all about isolating a variable and injecting it somewhere else. Step 1, take the simpler of your 2 equations and rearrange it so one variable is entirely by itself on one side. Step 2 is where the magic happens. You take that resulting expression and substitute it directly into the other equation. Just like that, you're down to one single variable, which you easily solve in Step 3, before finally substituting back in Step 4 to get the whole picture. Here's a perfect example of when to use this strategy. Our equations are 3x minus y equals -10, and this incredibly helpful x equals 2 minus y. Notice that the second equation already has x totally isolated. We already know that x is exactly the same thing as 2 minus y. So we just take that entire expression, 2 minus y, and drop it directly into the x spot in the first equation. We get 3 times the quantity 2 minus y equals -10. Boom! We've successfully created a completely manageable equation with only one variable, y, left to solve. Now for section 4, tackling nonlinear equations. Let's step it up a notch. So what happens when one of our mathematical paths is actually a curve? Can we still use the exact same algebraic tools when we're trying to find where a straight line intersects with a curved shape, like a parabola or a circle? With linear equations, straight lines usually cross exactly once. But a straight line cutting through a U-shaped curve, that might cross twice, or maybe not even cross at all. Well, the answer is yes. We can absolutely still use algebra here. And honestly, substitution is uniquely powerful for this exact scenario. Look at our two equations. The first one has an x squared, which tells us right away it's a curve, specifically a parabola. The second is a standard straight line. Because both of these are already neatly set to y equals, they are perfectly primed for substitution. We literally just set the x squared expression equal to the 2x plus 8 expression. We are mathematically asking the universe, at what exact coordinates do these two paths occupy the exact same space? Let's walk through the actual steps of how that plays out. By substituting, we set them equal. Next, we simplify by moving everything over to one side to create a quadratic equation set to 0. X squared plus x minus 6 equals 0. By factoring that quadratic into x plus 3 and x minus 2, we find two separate answers for x, -3 and +2. We then just plug those x values back into our simple straight line equation to get our y coordinates. The math flawlessly proves that there are two distinct points of intersection. The straight line crosses our curve exactly twice, at the coordinates -3, 2, and 2, 12. Finally, let's bring it all home with section 5, real-world applications. Think about an everyday problem, something totally relatable, like taking a taxi. The source text gives us this great scenario. A taxi firm charges a fixed fee just to get in the car, plus a rate for every single kilometer driven. Now, you don't know either of those rates, but you do know a 3-kilometer journey costs $4.60 and a 7-kilometer journey costs $9.40. This perfectly translates into simultaneous equations. We can set f as our hidden fixed fee and m as our unknown rate per kilometer. Suddenly, we have two equations working together. F plus 3m equals 460, and F plus 7m equals 940. Now, notice how both equations just have a single positive F sitting right there? This is absolutely screaming for the elimination method. By mathematically subtracting the first equation from the second, the F's cancel out completely. We're left with 4m equals $4.80. This instantly tells us that m, the rate per kilometer, is $1.20. Plugging that back in reveals our fixed fee F is exactly $1 flat. So if we want to calculate the cost of a brand new 6-kilometer journey, we take our $1 fixed fee, add 6 kilometers at $1.20 each, and we get the exact answer, $8.20. The unknowns are completely solved. How cool is that? So to wrap up our strategy for today, let's just quickly review the best practices. When you're dealing with straight lines, meaning two linear equations, use the elimination method. It's fast, it's efficient, it gets the job done. However, rely heavily on the substitution method when curves or nonlinear equations are involved. It's by far the safest way to break down those complex terms. And finally, the golden rule of algebra. Always, always check your calculated values by plugging them into the opposite equation. If both sides match, you know with absolute certainty that your answer is 100% correct. I'm going to leave you with a bit of a provocative thought to ponder. Mathematics isn't just a bunch of numbers on a page. It's literally a language we use to describe the world around us and uncover hidden truths. So what hidden variables in your own daily life, your finances, or your personal projects are just waiting for the right equations to be solved? Thank you so much for joining me on this explainer, and keep uncovering those hidden intersections. Catch you next time.